right, guys, we're going to do a couple more examples on section 2.6 on related rates, okay? All right, so this one asks us to find the rate of change in the angle of elevation of the camera shown in the figure at 10 seconds after liftoff. It says the velocity of the rocket is increasing at a rate of 100 feet per second. All right, so here's my step 0. Is that I'm going to have this little picture. I know there's one here. But I noticed that it's talking about an angle of elevation. We know that's measured from the horizontal. And they've labeled this S here, okay? And again, they're talking about the velocity of the rocket. And again, the rocket is going straight up. So the velocity is going to be related to this S, right? It's going to be the derivative of that. And some other information that you might want to know in the problem, remember it says that it's shown in the figure. And in the figure, it does say that the camera is 2,000 feet from the launch pad. So that's not something I could see by looking at the picture. I think it's in there, but you just can't see it because of the way it recorded or the way it copied. But essentially, this is going to be 2,000 feet. Okay. And then they kind of give you a clue in the picture of what to use because we're talking about this side and an angle. What we could do as far as the equation goes is maybe use what deals with our opposite and adjacent tangent. So we could say, all right, let's maybe try the tangent of theta equals this S, which again is a distance, right, over 2,000. All right, the next thing that we talked about identifying in these problems was a given rate. And the given rate is the velocity of the rocket is increasing at a rate of 100 feet per second. So the rate of change of the velocity is going to be 100 feet per second. And then they want us to find the rate of change in the angle of elevation. So I call that theta lovingly. So I'm going to find d theta dt, and then it says 10 seconds after liftoff. So when t equals 10. Okay, so that's the information that I have in the problem. Okay. Now remember that step 2 has us differentiate, so with respect to t. Oops, sorry. Got excited about the t there. We're going to differentiate this equation that we had, that the tangent of theta is going to be s over 2,000, and differentiate that with respect to t. Okay. So remember that when I take the derivative of tangent, that's secant theta squared. So I'm going to have secant square theta, and then again times d theta dt, since it's in respect to t. And I can pull out this 1/2000, and that is going to be then ds dt. And we could try, let's see, we're finding d theta dt, so we want to isolate that. So I will need to get rid of this secant square theta. So remember that secant is the reciprocal of cosine. Multiply both sides by, by cosine square theta. And then that would give me that d theta dt equals, I'll put cosine square theta over 2,000, or you could put 1/2000 cosine square theta ds dt. Okay. So now it's time for us to substitute things in, right? Here's step 3. Well, what we knew is we knew dv dt, but unfortunately it's not in our equation. All right, okay. So what we need to do is find what we need here. So we now know that we also need cosine theta and ds dt. So those are some things that we need to know. All right. So now that we have this expression for d theta dt, we now know that we need to somehow find cosine theta and we need to know ds dt. So how could we find cosine theta? Well, why don't we go back to the triangle that we dealt with, right? So for cosine theta, let's use the triangle. We knew in this triangle, I don't know why I keep drawing it, is that we have S and 2000, and this is our theta. Well, if we want cosine theta, or if we wanted cosine, we're going to have to do adjacent over hypotenuse. So that means we're going to have to find what our hypotenuse is, right? And that's not that bad to do. If we're going to find our hypotenuse, we're going to take the square root of s squared plus 2000 squared. So I'm just going to make a note that that's here, that this is going to be the square root of s squared plus 2000 squared. You guys agree with that? Okay. So let's do that with cosine theta. So cosine theta is going to be our adjacent, which is 2000, over the square root of s squared plus 2000 squared. Okay. The problem here is that we seem stuck again because we want a value for cosine theta, but we need s. So it looks like we're kind of stuck, right? However, they actually give us some information about s. They tell us, because again, remember that it was according to the picture. And another thing that the caption of the picture told us is that the position is actually being given by s equals 50 t squared. So what that means is that we can use, so I'll make a little note that, but we need s, okay? So we're going to use that s equals 50 t squared. And don't we know t when t is 10? Again, we've differentiated, so now it's legal for me to put that in. So my s is going to be 50 times 10 squared, and that's going to give me 5,000. And so now that we know that that's 5,000, now we can put it in here. So I know that cosine theta is going to be 2,000 over the square root of 5,000 squared plus 2,000 squared. And so that's 25,000 and that's 4,000. So this is going to be 2,000 over 29. Oh no, that's going to be 25 million. So 29 million. Sorry, I have to triple or double the zeros too. So we've got 25 million and then 4 million. So putting that together, we've got 29 million. It's a big number. Okay. So now I've got cosine theta. All right. Now I'm going to need ds dt. Well, again, what we know from here is that s, oh, here we go. Okay, good. S equals 50 t squared. So let's differentiate with respect to t. This equation. So if I differentiate this with respect to t, I get ds dt equals 50 times 2t. Oh, good, they match. We have the same variable. So that means that ds dt is 100t. Okay. Now, the thing is again, when t equals 10, that means ds dt is going to be 100 times 10. So ds dt is 1,000. And so now that we have that information, now we can put all that together here, which you can't see. So again, we said that d theta dt was going to be, I'll write it again, cosine squared theta over 2,000 times ds dt. So now let's put those pieces that we just found in. We found that the cosine theta, I don't know if you can see it here in the corner, was 2,000 over the square root of 29 million. And then we'll put that over, oh, we have to square that. And then over 2,000. And then our ds dt we found was 1,000. Okay. So then we just clean this up. So I can square this whole thing. So I have 2,000 squared over 29 million all over 2,000 times 1,000. I could multiply numerator and denominator by 29 million. So that gives me 2,000. I do have this times 1,000. And then I have this 2,000 and then times the 29 million. So this is just, you know, I'm just doing simplification here. Then I'll simplify this a little bit, that this is like one of these 2,000s can cancel. So essentially I have 2,000 times 1,000 over 29 million. I mean, you could put this in the calculator, I guess, and simplify faster. That you can cancel 1,000 from the 2,000 and then 1,000 from the 1,000 to really get that this is 2 times 1 over 29. And so what that tells us is that my d theta dt is going to be 2 over 29. And this was dealing in, remember, if we don't know the unit of an angle, we assume that it is radians. And again, t was measured in seconds. So my d theta dt is going to be 2 radians per second. Okay, that was a doozy, huh? We had a lot of information. This could have been attacked differently also, but I just wanted to give you an idea of when you see something, like kind of what you can deal with in the problem. Like if you come to a dead end, that sometimes you can go back with the different pieces of the problem and go forward. Okay, again, could be attacked differently. This is just another option for us. All righty. Okay, so example 7. All right. All right, these, once you, I didn't like these at first, but once you get in the groove of them, this one's not as bad. Example 7 says a man that's 6 feet tall walks at a rate of 5 feet per second away from a light that is 15 feet above the ground. When he is 10 feet from the base of the light, A, at what rate is the tip of his shadow moving? And B, at what rate is the length of his shadow changing? Okay, all right, so let's draw another picture for this. I know that we have one here, but I'm gonna try to mark it up because you can't really see anything because this is all dark from the copy, okay? So in this problem, guys, we know that the lamp post is 15 feet above the ground. So we know that this is 15 feet. All right. And here's the dude here that's 6 feet. okay? And what's happening is that we have these similar triangles that are here. And essentially, we have, and again, this is just a picture at one point in time. Yes, he is always 6 feet, okay? But what's happening is that we're going to call, I found it's called the part between here and here A, and this part here B. I think you'll see why in a little bit. Okay. When this is the person, his shadow, where's the color I don't use? Green, I don't use often. Like this is his shadow here. Okay. So what's happening is the light is shining on him, and then that's creating the shadow over here. So it's important for us to know that this is the shadow. And then in that regard, so the tip of his shadow is going to be represented by B, okay? So wherever B is, that is where the tip of his shadow is, okay? So B, whatever this length is the tip of his shadow. A is the distance from the lamppost to the dude. B is representing where the tip of the shadow is. And then the length of the shadow itself is going to be represented by B minus A, okay? Again, some of y'all could have gotten all that on your own. I know for me, I have to be told and then I kind of understand what to do. All right, so let's deal with letter A first. Let's deal with the tip of his shadow that's moving, all right? One thing that I can do is I see that I have I guess in both of them, I've got similar triangles that are going to be happening because the man and the light post are going to be parallel to each other. So we have these similar triangles. And so if we took, for example, the 2 dimensions that we have names for, I'm going to call this B minus A. And so B minus A over, I guess we could use the same triangle, over 6 is going to be the same as this length B over 15. Okay, you also could have put B minus A over B equals 6 over 15. It ends up being the same because to help us, we're going to cross multiply. And when you cross multiply, that's when we get 15B minus 15A equals 6B. And I guess we would want to know, okay, would we want to isolate A or would we want to isolate B? Well, again, we said that B was representing where the tip of the shadow was, so maybe let's isolate B instead. And so that says that 9B is going to be 15A. If I move the 6B over and the 15 over, and then I get 15A over 9, which is going to be 5/3 A. Okay, so that's my equation that I can get from this information, just the idea of the similar triangles. So now I want the given rate. All right, so the given rate that I have here is that he's walking 5 feet per second away from a light. And so that is how, so this A is changing. That's kind of what's happening, is that this is how he's moving away from the light, is this distance A. So for my given rate, that's going to be dA dt, and that's going to be 5 feet per second. And in letter A, it's asking at what rate is the tip of his shadow moving. So this is asking me to find dB dt, okay, because again, the B is going to be like where the shadow is. So I know that looks like a length, but really where B lands is where the tip is. So we want to find dB dt. And again, it says when he is 10 feet from the base of the light. So when he is 10 feet from the base of the light, so that's when A is 10. Okay. So let's differentiate that. So here's all of our information in step one. Let's come over here and differentiate this equation. Let's take the derivative of b equals 5/3 a with respect to t. So I can see that gives me that db dt equals 5/3 and then dA dt. Okay, that's step two, good. And now we have step three. Step three is where we're going to put that in. So dB dt equals 5/3. dA dt was this 5 feet per second. Oh, it doesn't look like we needed the A equals 10 at all, did we? So we can say that dB dt is going to be 25/3, and our unit would be feet per second. Okay, so that's letter A, the tip of his shadow is moving. The next thing it asks is at what rate is the length of his shadow changing? And so it's at this point when, so that's our letter A. So in letter B, what it really wants us to do, we still have the same information, but this time it's asking us to find when the length of the shadow, which is B minus A, is changing. So that's really going to be the derivative of B minus A given, with respect to t. Well, let's think about what we could do with these derivatives. One creative thing that you could do is to use the rules and see that this is really going to be the same as dB dt minus dA dt. And again, now we knew what dB dt was, right? Didn't we know that dB dt was 25/3? And here we knew that dA dt was 5. So we could take 25/3 minus 15/3, which is 5, and that gives us 10/3. So that means that the derivative of B minus A with respect to t, and again, this is the shadow, the rate of the change of the length of the shadow, is going to be 10/3 feet per second. So, okay. So I know I didn't leave much room for B. We really didn't need it as far as that goes, because we were able to use our previous information. Okay. Example 8, last one. I don't know why there's a delay. All right, in an engine, a 7-inch connecting rod is fastened to a crank of radius 3 inches. The crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Find the velocity of the piston when theta equals pi over 3. Okay, so here is our picture. I'm not going to draw another one this time because we don't have lots of room. All right, but here we have our picture, and notice it says that we have a 7-inch connecting rod. So here is our connecting rod that is 7 inches. And then this is the crank with a radius of 3 inches. So that's my radius. And it says it rotates counterclockwise at a constant rate of 200 revolutions per minute. That sounds kind of promising. The crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Okay, so that's a revolution. We don't have any revolutions in this problem. I wonder what we could do. I don't know. And then it wants us to find the velocity of the piston. All right, and the velocity of the piston, remember, is going to be the derivative of the distance of the piston. And that's what's happening here. That's what this x is, you guys. X is going to represent the distance that the piston is moving. And again, the velocity is the derivative of the distance. So if it wants the velocity of the piston, then that's looking for dx dt, essentially, okay? So we have a couple things that we want to do in our setup, right? So that's our step 0, is that now we need an equation, and then we need a given rate and what we want to find. So if we think about an equation, we might be like, what the heck? We have these 3 sides and we have this angle. Well, you guys, when you have 3 sides and an angle in a triangle, when you have a case like this, this is where you can use the law of cosines. Haven't we done that before? So we have information about 3 sides of a random triangle and the other side. And again, we're looking for like this angle theta. So in the law of cosines, we use the side across from it kind of as our basis. So we're going to have 7 squared equals, and then we can say, I don't know, 3 squared plus x squared minus 2 times 3 times x times the cosine of theta. So then we can, I guess, deal with the constants a little bit. And this is about as simple as I can make it. 40 equals x squared minus 6x cosine theta. So there's my equation. So the variables that we're really concerned with are x and theta. And you might say, okay, well, I don't really have a lot of information about theta, except this was talking about rotating. When it's talking about rotating 200 revolutions per minute, that's really telling us about theta, isn't it? About the rate of change of theta, because how many radians are in a revolution? That's right, 2 pi radians. I'll just be dramatic. 2 pi radians are in 1 revolution. So what this is really telling us is that this is 400 pi radians per minute. And that's going to be our known rate. So our given rate is going to be the rate of, is that radians per minute. So that is the rate of change of theta with respect to t. That d theta dt is going to be 400 pi radians per minute. And again, they're asking for the velocity. Remember that the velocity is the derivative of our distance. And so that means that we're going to want dx dt. That was the distance the piston was moving, and they want the velocity of the piston. And in particular, they want this velocity when theta equals pi thirds. Okay. All right, so now what we're going to do is take the derivative with respect to t. So we're going to take d dt of this 40 equals x squared minus 6x cosine theta. Okay. You see this is going to get a little messy here. So notice we've got x, we've got theta, and we were taking both of these with respect to t, but it's going to be okay. All right, so let's use all our knowledge of derivatives and let's go to town. So we know that this is a constant, that's 0, that's nice. All right, now we need to take the derivative of x squared with respect to t. So that's going to be 2x dx dt. Now we're going to have to use the product rule. I'm going to pull the 6 out if that's okay. And now I'm going to use the product rule on x times cosine theta. So I need to take x times the derivative of cosine theta with respect to t. Do I need to write all that down? Okay, so I'm going to do x times the derivative of cosine theta with respect to t. So the derivative of cosine theta is going to be negative sine theta, but with respect to t, I need to include the d theta dt, and then plus, and now I'm going to use cosine theta times the derivative of x with respect to t, which would be dx dt. Okay, so let's maybe see what we can do here. Maybe now I'll distribute the -6 that I have here. So this becomes positive 6x sine theta d theta dt, and this becomes minus 6 cosine theta dx dt. Now, what was I trying to find? I was trying to find dx dt. So that tells me that I'm going to move all the dx dt's over to the left. Okay, that's how I know. People are like, how do you know if we want this or that? Well, that's why we have this find. That tells us that we're going to put all the dx dt's to the left. So I'm going to put this one on the left first so that it's positive. So 6 cosine theta dx dt. And now move this guy over, minus 2x dx dt. And then that's going to equal 6x sine of theta d theta dt. Okay. And just like we did with the implicit differentiation, we can factor out the dx dt. So that's 6 cosine theta minus 2x equals 6x sine theta d theta dt. So dx dt is going to be 6x sine theta over 6 cosine theta, oops, minus 2x times d theta dt. Okay, these are both, do you guys see that all these three terms are even? So we can divide them all by 2 because we have nothing better to do. And we're going to get 3x sine theta over 3 cosine theta minus x, and then d theta dt. Okay, so let's think about what we would do in step 3. In step 3, we're going to want to substitute these different pieces in. So let's see. We are going to need something for x, and we've got d theta dt, and we've got theta. We don't have x. Okay, so we look here that we're going to need x too. Okay, so we're going to need to find that somehow. So again, we can use the equation to help now that it's legal. After we differentiate, now it's legal for me to use the equation to help. And now I can put this in. So I have 40 equals x squared minus 6x cosine theta. And remember, we're doing this when theta equals pi thirds. So 6x times cosine of pi thirds. Okay. So 40 equals x squared minus 6x cosine of pi thirds is 1/2. Oh, that's super nice. So is this going to be factorable? Oh my gosh, it's like algebra 1. Look at these memories, all right? So we're going to get one side equal to 0, and then we can factor, and then this will give us some possibilities for x. We get that x could be 5, or x could be -5. And again, x is the distance the piston's moving. So at pi thirds, this -5 isn't going to work, so it must be this 8. So now we can use this as well. So now we've got the pieces to put in to this dx dt. So dx dt is going to be 3 times x, which is 8, times the sine of theta, which is pi thirds, over 3 times the cosine of pi thirds, minus x, which is 8, times dx dt, which is 400 pi. Okay. And then we just keep going there. So this is 24 times root 3 over 2 over 3 times 1/2 minus 8, again, times 400 pi. This light is so annoying, sorry. So I could multiply this together. This would be 12 root 3, if that cancels. And then 12 times 400 is 4,800 pi, and then root 3. And then this is 1/2 minus 8. So that's going to be negative 6.5. Again, since that's a half, I could just multiply everything by 2 and get 9,600 pi root 3 over 13 for my dx dt. Again, it's asking for the, this one is asking for the velocity, so that's okay. We can leave it negative. If it was like speed, we wouldn't, but velocity, we can have it be negative. And if it wanted an exact answer, we could divide to see what that is. So we could take negative 9,600 pi root 3, oh, this is an old school one, and divide it by 13. And that gives us about negative 4,018. And our units are in inches, yes, inches per minute. And I'll leave them both, just in case. If it tells you to round to the nearest inch per minute, if it says give an exact answer, that's what we do. All right, so that's a little bit about related rates. And look, that means we're done. And to be honest, like the related rates, like it's heavy, all right? Like it gets better after related rates, if that makes you feel any better, okay? But that's it. The best thing to do is just to kind of practice, look for patterns, and just keep your chin up, okay? Again, the more you do, the better you'll get at it. If you need more practice, let me know. Happy calcing.